What's up, everybody? We're on lesson number 5 here, the counting principles. Before I start, as you can already see on your screen, there's word problems here. So what I would suggest is, once you see a new problem, pause the video and write down whatever it says if you're taking these notes, okay? Just as a heads up. So let's get right into it. First of all, we have the count, okay? A count is just the number of ways an event can happen. An event could be anything. An event could be, putting your clothes on in the morning, or it could be a race between cars or something, or it could be pulling numbers. It doesn't matter. That's all an event is. So it's the number of ways something can happen. So we're just going to get right into some examples here. Okay, 2 boxes contain numbers 1 through 10. If you randomly pull a number from each box, how many different ways can you obtain a sum of 12? So let's think about what's happening here. We've got box 1 and box 2. We want to add 2 numbers that I pull, one from here and one from here, to make them equal 12, right? So if I pull out a 1, I would have to pull out an 11 to add up to 12. But obviously our boxes don't contain those, so there's no way for that to happen. So that means the lowest number I could pick would be a 2, which would have to match with a 10 from box 2, right? 2 plus 10 is 12. And the next option, I could pull out a 3 plus a 9 from the second, and I could keep on going, so on and so forth. So I'm just going to list these all out here. Okay, and obviously I wouldn't choose an 11th because it's only going from 1 to 10. Let's see, by the way, is this allowed here? Sure, because I have 1 through 10 in each box, so I can pull a 6 out and a 6 out. So if I were to pull out 2 random numbers and add to 12, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 ways that that's possible. Okay. You're using the same system above, but this time you want a sum of 9. So try that one on your own, pause, and resume when you're ready to check. Okay. Box 1 and box 2. I can pull a 1 out because I can add it to an 8. I can pull a 2 and add it to 7, a 3 with 6, a 4 with 5, and then it starts to kind of go backwards. A 5 with a 4, a 6 with a 3, a 7 with a 2, an 8 with a 1. I can't pull out any 9s from either of these because there's no 0 to add to it. So these are all the ones that I want to check. There's 1, 2, 3, 4, 5, 6, 7, 8 ways that we can pull out a sum of 9 using that system. Okay, so far not bad, right? Let's mix it up a little bit. This time we have a jar containing the numbers 1 through 9. This time if we pull out 2 numbers without replacement, how many ways can we obtain a sum of 8? So here's the deal. You have your jar, you pull out a number. Let's say on your first pull, you pull out a 1. That means without replacement, you cannot pull out a 1 again in this this experiment, right? So if I pull out a 1, in order to get a sum of 8, I'd have to pull out a 7. If I pulled out a 2, I'd have to pull out from the second pull a 6. A 3, I'd have to pull out a 5. If I pulled out a 4 from the first pull, I would have to pull out another 4 to make 8. But that's not possible because I never put that 4 back into the jar to pull it out again, right? There's no replacement. So that one doesn't count. I could pull out a 5 and a 3 the second pull. I could do a 6 and then a 2, and then finally a 7 and a 1. So yes, I listed that double, but it's not able to happen. So the number of ways that we can pull out a sum of 8 without replacement is 6 ways. So here's one for you to try. Okay, very similar system. Jar contains 1 through 12. If you pull out two numbers without replacement, how many ways can you obtain a sum of 16? Pause the video and see what you come up with. All right. We've got pull 1 and pull 2. Remember, there's no replacement, so we can't have any repeats. If I pull out, let's see, I can't pull a 1 because I would need 15. That doesn't work. I can't do a 2 because I would need 14. That doesn't work. Can't do a 3 because that would be 13. If I pull out a 4, that would match with 12. If I pull out a 5, that matches 11. 6 and 10. 7 and 9. Uh-oh, 8 and 8 doesn't work. Then you got 9, 7, 10, 6, 11, 5, and 12, 4. So none of these were possible, even though I could pull out a 1, 2, and a 3, I can't pull out a 15, 14, or 13. They're not part of our system. So here are the ones that work. 1, 2, 3, 4. That doesn't work. 5, 6, 7, 8. So there you go. That is one type of accounting principle that we're going to look at. The next type that we're going to look at is the fundamental accounting principle. These are the kind of fun ones that have to do with like how much clothes you could possibly wear, that type of stuff, right? So the fundamental accounting principle, if you have event E1, your first event, could happen M number of ways. Who knows how many? We just looked at a couple of different situations. Then you have a second event that could happen M2 different ways. Okay, so these can be any numbers really. The number of ways that both events can occur, we're going to end up multiplying whatever we get for the happens. That sounds confusing. Let's look at an example of this. Okay, it'll be a little bit easier. So let's start off with the ones that you usually see in like elementary schools with clothing and stuff, right? You have 12 shirts, 4 pairs of pants, 5 shoes, all in your closet. We want to know how many different outfits could you wear. Now, each of these things, right? A shirt, putting on a shirt, that's an event, okay? And we can put on our shirt 12 different ways, right? There's 12 different shirts we could possibly put on. So for our first event, we have 12 items that we can wear. Our second event would be putting on pants, and it tells us that we're multiplying. So for pants, we have 4 different things that could happen, right? We could put on 4 different types of pants. Finally, you have your shoes. You have 5 different shoes that you could be wearing. Okay, so if we multiply 12 times 4 times 5, let's see, that's 20. That'd be 240. So you have 240 different outfits that you could wear with 12 shirts, 4 pairs of pants, and 5 shoes. Let's take a look at a different one. Okay, this is a little bit different. This time, we want to know how many 3-letter pairs can you make using the alphabet. Some information we need to know, like how many letters are in the alphabet. There's 26. Okay, so let's see. We've got 3 spaces, right? 3-letter pairs. There's 26 letters in the alphabet. So I could choose any of the 26 here. I could choose any of the 26 here, and I could choose any of the 26 here. And if we multiply 26 times 26 times 26, you end up getting 17,576. So I'm just going to throw a couple out there, right? You could have AAA, AAB, AAC, AAD, right? And we would go all the way until we get to ZZY, ZZZ, right? there'd be 17,000 different of those that you could possibly list. It's a lot. Okay, let's look at one that has to do with lockers, locker combinations, right? A locker combo uses 4 entries with digits ranging from 0 to 15. So you've seen the spinny lockers before, right? And they have numbers around them. So you're going to end up having 4 entries from 0 to 15. We want to know how many different combinations there could possibly be. Okay. Well, we have 4 entries. If I include 0 as a digit up to 15, that would be a total of 16 digits that I can use, because 0 is included, and then 1, 2, 3, 4, 5, all up to 15. So there's actually 16 digits that I can use here. Now a locker combo is neat because you can repeat digits, right? You just spin it one way and then spin it the other. So we've got 16, 16, and 16 for each of these entries. These are all the possible numbers that I could choose. And if we multiply 16 times 16 times 16 times 16, we get 65,536. So this is a pretty good locker combo, right? Let's say that you catch somebody in the hallway messing with your locker and they're randomly guessing. They have a long time to be guessing, right? They have a lot of different numbers to guess. So you're probably going to catch them in the act of trying to break into your locker. That's the case. So, got one of these for you to try. You're rolling 3 standard dice. A standard die has 6 sides. So my question is, how many different combinations can you roll? Pause the video and resume when you're ready to check. All right. We have 3 dice. That's my first die. That's my second. And that's my third. And I know that each of these things we're going to end up multiplying. There are 6 sides per die, right? So that means I could get anywhere from a 1 to a 6 here. My second die I could roll anything from 1 to 6, and my third as well. So I'm going to be doing 6 times 6, which is 36, times another 6, which is 216. So there's 216 combinations you can roll with 3 dice. That's a lot. Okay, let's take a look at a different one. A new phone company is creating 3-digit area codes, but there are some restrictions. The first digit cannot be a 0 or a 1, while the last digit must be odd. How many area codes are available? Well, let's think about each of these events, right? We have 3 digits in our area code that we can work with. And think about a phone, right? A phone goes from 0 to 9. So there's actually 10 digits that you can choose, right? But we can't use the 0 or the 1 for the first digit. So really we have to go from 2 to 9 for that first digit, which is a total of 8 that we can choose from. The middle doesn't actually say anything, right? We can use anywhere from 0 to 9. So that's a total of 10 digits that we can use for the middle. The third one, though, it says it has to be odd. So we have to choose 1, 3, 5, 7, or 9. Those are the only odd numbers that we can put here. So that's a total of 5. So I have 8, 10, and 5 for each of those digits. And if we multiply, 80 times 5 is 400. So there are 400 area codes that this phone company can work with. As far as giving out or creating a map, I guess. I'm not sure how they work with phone companies. Anyways, got one for you to try. Pause the video and resume when you're ready to check your solution. All right, so let's check this one out. It says that the state of Delaware is making new license plates. They want a 4-digit number followed by 2 letters with no repeats anywhere. It's kind of close to Rhode Island, Delaware, trying to steal our license plates. Pretty close. Not the same, though. Anyways, so let's check it out. We have a 4-digit number followed by 2 letters. So we've got 6 things that are going to show up on those Delaware license plates. We can use anywhere from 0 to 9. That's single digit numbers. So 0 to 9. That's a total of 10 different numbers that I could have show up first. But we don't want to have any repeats. So that means that if I chose one of these numbers, it doesn't matter which one, there's only 9 left to choose from. And again, if I already used these two numbers, wherever they happen to be, that means I only have 8 left to choose from. And finally, for my fourth number digit, I'd only have 7 left to pick from. Okay, no repeats here. Then I want to have my 2 letters. Okay, the alphabet we talked about before has 26. And if I choose one of those letters, let's say we pick L, that means that there's all the other numbers left to work with besides that L that we just chose, which means that there are 25 left. Okay, so that is our setup. You need to multiply all of these things together. And I got 3,276,000 different license plates. There's not even that many people in Delaware, if I'm correct. Maybe I'm wrong, I'm not sure. I could probably check it, but that's a lot of license plate for one state to have. Anyways, let's move on to something called a permutation. A permutation is the number of different ways elements can be listed in a specific order. Okay, this is important for permutations. Permutations, order matters. We're talking about things like racing, right? First place matters compared to third place. You get a nicer, shinier trophy for first place than you do for third. So order matters. And it's not just races. We have things like rainbows, right? We have rainbows that contain the colors in this order: red, orange, yellow, green, blue, indigo, and then violet, right? And red is on the outside, and purple colors are on the inside. So the question here is, how many permutations of unique rainbows are there? Okay, well, we have 1, 2, 3, 4, 5, 6, 7 colors that we can choose from, right? So there are 7 spots that we can fill in with any of those colors. And seeing as there are 7 colors to choose from, we know that there are 7 options for the first. But because order matters, if I chose one of those to be first, that means that I can only have 6 possible for the second color. And then that would mean that I'd only have 5 possible for the next color. And then only 4, and then 3, and then 2, and then you're forcing that last color after you've chose all of those. You only get 1 left. Okay, so those are all the different possibilities. And if we multiply those, we get 5,040. So basically, I could take and rearrange all of these 5,040 different ways. That's how many different possible rainbows could show up, I guess, if physics didn't work the way that it does. They have to be in that order, but this is just, I don't know, maybe you're making stickers or something, or drawing a card for somebody. Okay, let's look at one that's a little bit more realistic. Right, 8 cars are in a race. How many permutations of first, second, and third place are there? Well, this one's only asking for first, second, and third. First place, second place, third place. Now, what's nice is, as far as getting first place, there's 8 possible cars that could win it. Right? But once I take first place and take that car out of the equation, that means that there's only 7 other cars that could possibly take second. And then the same thing would go with third. I'd only have 6 cars remaining to take third place. Now, I don't care about 4th place or 5th place. They're only asking about first and third. So these are the numbers that I need to be multiplying for my permutation, and we end up with 336. So 8 cars, we could have 336 different first, second, and third place finishers. Okay. So I've got one for you to try right here. Pause the video and resume it when you're ready to check. Alright, I gave you ice cream because I figured it was more interesting than cars. You're doing a taste testing of 10 new flavors of ice cream. You need to pick your top 4 favorites. How many permutations of the top 4 flavors are there? Alright, well, we've got our 4 placements. Out of the 10 flavors, you can choose any of the 10 to be your number 1 favorite. But once you choose one to be your favorite, you've only got 9 left to choose from for your second, 8 left to choose for your third, and then 7 left to choose for your fourth. And if you multiply all of those together, there are 5,040 unique permutations that you could choose for your top 4 favorites. Why does that matter? Let's say that you're doing a survey of ice cream flavors around the country, and you send out like millions and millions and millions of different surveys for people to try. You want to have an idea of how many different results you can get back. That's the most different unique results you could possibly get back on that survey, which is good to know, because then you can start doing things like probability. Okay, we're not going to get there quite yet. That'll be the next lesson. But let's work a little bit more with permutations. We saw in the lesson prior to this, binomial theorem, something called n choose r. Now we're doing something called NPR, which works with permutations. Okay, so you have NPR, n factorial divided by n minus r factorial. Very similar to the n choose r. Your n is the number of elements, and r would be the number of events. Right? These are elements, and then each of these would be your event. Okay? So let's try one out with some larger numbers, because if we end up getting larger numbers, the formula will help cut down our work a little bit. Okay? We have a horse race with 16 horses running, and the top 5 placers will win a prize. So the question is, how many permutations are possible? We're not going to write down the things this time. We're going to do 16 permutations of 5. All right. It said take your n value on top, and then you're going to do n minus r factorial on bottom. So that's 16 divided by 11 factorial. Just like I did in the binomial theorem lesson, I'm going to expand this as much as I can until I get to this number here. So that's 16 times 15 times 14 times 13 times 12 times 11 divided by 11 factorial. You notice that your 11s go away, and then we have 16 times 15 times 14 times 13 and times 12. If you multiply all of those together, you end up with 524,160. So, again, who cares? When we start talking about probability, a lot of people care about horse racing. That's something that you can bet on. And then they can start talking about odds and stuff like that as well. Okay, so you're going to try this one. There's a club with 13 members. How many permutations of president, vice president, and secretary are there? Pause the video and press play when you're ready to check. All right. We're doing 13 permutations of, let's see, there are 3 places. Okay, so we're doing 13 factorial over 13 minus 3 factorial, which is really 13 factorial over 10 factorial. So when I expand this, it's going to be 13 times 12 times 11 times 10 factorial divided by 10 factorial. So I'm going to get rid of those 10 factorials. 13 times 12 times 11 is 1,716. So for a club with only 13 people, that is a different number of ways that you could have a president, vice president, and secretary. And Anybody who's ever worked with little kids knows that one day somebody has to be the president, and somebody else has to be the vice president, and somebody else has to be the secretary. If you were to give each of these kids an opportunity at each position, you'd have to meet that many times in order to fulfill that requirement. Okay, starting to see why these counting principles are coming in handy. Then you got something like this, distinguishable permutations. If there are multiples of an element, like n1 of one element and 2 of a second element, what we're going to do is we're going to take the total number of elements factorial divided by however many of that element factorial times how many of that factorial times how many of that element factorial. Okay, it's going to make more sense when you look at this example down here, right? You see here how many distinguishable ways can the letters in Bumblebee be written. Okay, first of all, the n that we're talking about here is the number of letters in total. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So our n value here is 9. Now, for each of these letters, I need to know how many there are. I have 3 B's. I have 1 U. I have 1 M. I have 1 L. And last, I have 3 E's. Okay, I've covered all my letters now. If you need to cross them out while you do it, go for it. I don't care. Okay. Now we got to figure out how many distinguishable ways we can write this. So my n value would be 9 factorial. And then I'm going to plug in for each of these, right? So here's one element. That's my n1. That'd be 3 factorial. U would be my n2. So that's 1 factorial. And then another 1 factorial. And then another 1 factorial. And finally, 3 factorial. So these 1, 2, 3, 4, 5 matches with my 1, 2, 3, 4, 5 different letters. All right. Well, I'm going to get rid of some stuff. Right, these 1 factorials are kind of boring, right? 1 factorial is just 1. 9 factorial, I'm going to write as 9 times 8 times 7 times 6 times 5 times 4 times 3 factorial. And I'm going to expand this one. 3 times 2 times 1. We left those on purpose so we can get rid of those. 3 times 2 is 6. So that goes. What we're left with is 9 times 8 times 7 times 5 times 4 divided by 1. So if we multiply basically whatever's left on top here, we're going to end up with 10,080. That's how many different ways, distinguishable ways, you can rearrange the letters in Bumblebee. What does that mean? Well, notice how this B is the first B here. It doesn't matter which of these two or any of these B's is the first one. But we could start rearranging all these letters, and we could have a B and then an M here, for example, or an L or something, right? But the distinguishable thing means that we're not going to change this B with another B. Why would this matter? Not only is it really fun to work with letters, like words with lots of repeating letters, it's just kind of fun, like Mississippi is a good one to look at, but sometimes you have like contests or games at parties or something, and you're giving out prizes to people that have like the same first initial or something like that. There's all sorts of different ways that we can look at this, different examples, but that's something that could possibly show up. Okay, so you got one here to try. How many different ways, distinguishable ways, can the letters in iced coffee be written? Pause the video and resume it when you're ready to check. Alright, so I've got, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 entries total. That's my n value. Then I'm going to work with each of these individual. I've got 1 I. I've got 2 C's. I've got 1, 2, 3 E's. only one O and two F's. So we want 9 factorial divided by 1 factorial times 2 factorial times 3 factorial times 1 factorial times 2 factorial. Okay? Getting rid of some stuff that doesn't really help, the 1 factorials, those go. This 9 I'm going to expand. 9, 8, 7, 6, 5, 4, 3 factorial. That's my largest one. On the bottom I've got 3 factorial. I'm going to put first. I'm going to expand each of these. Times 2 times 1 times 2 times 1. 3 factorials, those go. 2 times 2 is 4, so the 2's and the 4's go. So I'm multiplying 9 times 8 times 7 times 6 times 5 divided by, that's just going to be 1. So if I multiply all those on top, we get 15,120. So there's 15,120 distinguishable ways that you can rearrange the letters in iced coffee. All right, this is going to be the last thing that we look at is combinations. When order doesn't matter, we use combinations. Different from permutations, right? Permutations, we said that order mattered. Combinations, we don't really care. These would be things like sitting people at tables. No one cares what chair you're sitting in. There's no position for your chair. It's just people sitting at a table. There's other stuff too. Prizes at entries to places, door prizes, right? Those are things that it doesn't matter. People are just winning things, okay? So that's what we would think of with combinations, just things where order doesn't matter. We're still using our n choose r formula from before, so it's n factorial over n minus r factorial times r factorial. N would be the number of elements, r would be the number of events. So these are our last two problems. If you want to write them down real quick, we're going to go over them right now. All right, so we've got 10 people in a cafeteria are searching for seats at lunch. One of the tables has only 8 chairs. So the question here is, how many combinations of people can sit at the table? Obviously, not everybody's going to get to sit down, right? 2 people are going to have to find somewhere else to sit. So what we're doing here is we have 10 total elements, but we're only seating 8. So we're doing 10 choose 8. All right, so that's 10 factorial over 10 minus 8 factorial times 8 factorial. Simplifying, 10 minus 8 is 2, so I put those in order. And I'm going to expand this 10 times 9 until I get to that 8 factorial. I am going to expand this 2 and 1 though. Okay, my 8 factorials, those all go. 2 will go into 10 5 times. So 5 times 9 on top is 45, just 1 on bottom. So there's 45 different combinations of people that could sit at that table. Okay, so you got 10 people standing around, 45 different combinations of who could be sitting at that table. Because remember, it doesn't matter where you sit at the table, it's just the fact that you get a seat there. Okay, so here's one last one for you to try. Pause the video and resume it when you're ready to check. All right, let's see how this one worked. You're at a party with 12 other people. That means you're included. I hope that you kept an eye on that. Okay, so there's, in total, there's 13 people. 5 people are going to win a door prize. If you know anything about door prizes, they're just like randomly selected. Maybe they pull out a ticket or something from a bucket. Who knows? But there's no first, second, third place. The order doesn't matter. It's just the fact that 5 people are going to win something. So the question is, how many combinations of winners could there be at this party? How many 5 people combos are going to walk out with smiles? Right? So we've got 13 factorial on top over 13 minus 5 factorial times 5 factorial. If we simplify a little bit, you get 13 factorial over 8 factorial times 5 factorial. So I'm going to expand that 13 until I hit that 8. And I'm going to expand this 5 all the way. Let's get rid of the 8 factorial. Let's see. 4 times 3 is 12. 5 times 2 is 10. So I've got rid of everything from the bottom except for the 1, which doesn't really matter. On top, I've got 13 times 11 times 9. 13 times 11 times 9 is 1,287. So you go to this party, 5 people win a door prize. It could have been any one of these 1,287 combinations. That's incredible. Who cares about that? Hey, there's a lot of jobs in the lottery around the state. All sorts of different things that you can look at with prizes and combinations. Okay, so these counting principles are used pretty much everywhere. And when we start getting into probability, which is really what you use counting for a lot of times, you're going to see that we want to know how to find the count of something. These principles will help us. So I will see you at lesson number 6, I believe, is probability, which is also the last lesson of this unit. All right, see you there.